We saw that virial equation using three terms was an example of a quadratic equation. You had z is equal to 1 plus b dash p plus c dash p squared. Another set of equations that provide for such quadratic behavior, that are able to replicate such behavior of a real gas, is the family of van der Waals equations. Now, the van der Waals equations is historically or traditionally an important equation because, unlike the virial equation where the parameters are just fitted to data, a van der Waals equation was based on the physicality of a problem. The van der Waals equation assumed that for a real system you have to account for the particles having a finite volume. Remember that an ideal gas assumes that the particles have no volume, so the particles are point particles, and that there is no interaction between these particles. Van der Waals attempts to replicate the behavior of a real system by saying that the particles actually do have volume, and since they have volume, one particle cannot come too close to a second particle. It can only, for example, come up to this point. Here, it could not overlap with the other particle. A certain fraction of this box in which these particles exist is excluded from other particles' ability to take up space. So this particle here cannot take up space where the other particles are already present. So that is one assumption that the van der Waals equations make. The second assumption the van der Waals equation make is that there is a finite interaction between particles. So this B term here represents the deviation or the reduction in volume owing to the fact that other particles are also occupying space, and this A over V squared term represents interactions between the particles. So van der Waals equations takes PV over RT, adds this space constraint to volume as well as this pressure because of interactions between particles. So van der Waals thus uses B, which is a measure of the excluded volume that accounts for the size of the molecules. It also accounts for the increase in pressure and density increase because of these interactions. So A is a measure of the attraction between the particles. With this model now, we can account for the behavior of materials at low to moderate pressures, accounting for the size of these particles as well as the interaction energies between these particles. This is another model that relates pressure, volume, and temperature and is more realistic than ideal gas model, and this is the van der Waals equation of state. So we can rewrite the van der Waals equation as P plus A over V square times V minus B is equal to RT, and we see that this is a deviation from PV is equal to RT. The deviations coming from A over V square term, which accounts for the change in pressure because of interaction between particles of the gas, and a minus B term, which comes from the fact that now the particles themselves occupy a certain volume, and hence the total volume for a particle in the gas must be lower by an amount B, which is volume occupied by the other particles in the gas. So I can rewrite this as PV square plus A times V minus B is equal to V square RT. And if I expanded this further, I would see that this has a V cube term, and hence this equation for certain values of temperature and pressure must have three roots or three values of volume. For a specific value of pressure and of temperature, there can be three values of volume or specific volume that satisfy this equation. So if I had a graph of P versus V for a certain value of temperature T, this curve would do this. We've drawn this for a value of temperature T. So for Psat for the saturation pressure at this temperature. There are three values of volume that satisfy this equation. We know that at saturation, at a given temperature and the saturation pressure at the given temperature, Psat at which this liquid boils. So we have the smallest volume, the smallest root of these three values of volume will be the saturation liquid volume, and this here would be the saturation vapor volume. Now for a different temperature, let's say that I choose a slightly higher temperature. I see that this higher temperature will have a, a Psat, a new Psat, or a new saturation pressure, which is also higher. And again, there will be three roots at this new temperature. And this will be the V liquid at this new temperature, or the specific volume of the liquid when this boils, and the specific volume of the vapor. I also noticed that these two roots are coming closer together as the temperature is going higher. Eventually, as I increase the temperature, I will have a curve that will look like this, where at the saturation pressure at this new temperature, I will have these three roots, these three volumes, one on top of the other. So this point here has three roots. All three roots are the same. And now I would see that if I drew a line connecting the smallest roots at these different temperature, I would get this. And if I drew a line connecting all the largest roots at these different temperatures, I will get that. So now I've been able to use the van der Waals equation to define my two-phase region. Thus, I show how the van der Waals equation is able to present trends of phase transformation. It's able to show the liquid phase and the liquid volume and the vapor volume, as well as how the liquid volume and the vapor volume come closer and closer together till I get to the critical temperature where I have a critical volume. So this profile of pressure and volume for this fluid is at the critical temperature. These ones were at temperatures lower than critical temperature, and at temperatures higher than critical temperature we'll only see a single fluid with no phase transformation at all. So at these temperatures higher than critical temperature, there will be no P saturation. Any pressure will only have one root. In the analysis so far, we've looked primarily at the smallest roots, and we've said that those were the saturated liquid volume roots, and we've looked at the largest roots, and we said that those were the saturated vapor volume roots. We've left the middle roots out. Really, as far as this analysis goes, we ignore those. Now let's take another look at this PV graph, and we already saw that the van der Waals equation was able to define this two-phase region, the liquid region and the vapor region. So we were able to get this information from the van der Waals equation itself. we saw that for a given temperature, this is the behavior we saw at saturation pressure. There were three roots. The smallest root was the saturated liquid, the largest root was the saturated vapor. And again, this was a pressure versus volume graph. Now for the same profile, for the same trajectory at temperature T, so this was Psat. At this temperature, for pressures higher than Psat, we may get 1, 2 or 3 roots. So right here, I'm getting one root here and a second root here. So for pressures higher than Psat, the root that really matters is the smallest root, and it gives us the liquid specific volume. I could choose another pressure still higher than Psat, and I would get this root here, and this root here. This again is the specific volume at this pressure and this temperature. I ignore the middle root as earlier. Now the third root here actually is a metastable root. It is a vapor volume root. This root is a volume of the vapor. However, it's a metastable volume. At pressures lower than Psat, the largest root gives me the vapor specific volume, and the smallest root here gives me a metastable state liquid volume. Again, at pressures higher than Psat, I get a liquid volume as the smallest root, and the largest root gives me a metastable state vapor volume. At pressures lower than Psat, I get the largest volume as the vapor state specific volume, and the smallest volume is the metastable state liquid volume. This metastable state liquid volume is a physical volume. If I was to carefully bring the pressure down, I could get into a supersaturated liquid state. It would not be a stable state. Any perturbation would cause it to flash. It would cause it to boil into the vapor volume. However, I could get it down here. So this is a metastable state. I would get metastable state liquid volumes up to the minima of this curve, and I would get metastable state vapor volumes up to the maxima of this curve here. If I took all of these curves and connected their minima, I would get a curve like this. So if I took these curves at different temperatures and connected their minima here, I would get a curve like this. If I took all the curves and connected their maxima, I would get another curve like this. And this region here is basically the region of spinodal decomposition. It is the region where I could get metastable properties or metastable states of this liquid vapor transition. So the van der Waals equation not only gives me the liquid roots, the specific volumes of the liquid state and the vapor state, it also shows me spinodal roots or spinodal state properties. Thus, a simple deviation from the ideal gas law, accounting for the volume of the particles and the interaction between particles, gives us a wealth of information. It's able to show the phase behavior of particles, transformation from the liquid to the vapor state. It's able to show us for a given temperature what the saturation pressure is, and it is able to show us metastable states as well.